60s and then in the 70s, and she could never kind of get the whole key put together. And, you know, when we met and I talked with her for almost 3 days, I was able to fill in a lot of things, but she didn't know, and we had to talk some more, and we had to run some calculations and all this, and she was definitely skeptical, but we started to write things, and then we thought, well, okay, if this is true, then if we look at a large scale in the universe, we should start to see very specific divisions. We should start to see structure. If the vacuum is dividing under very specific structure, then we should be able to see it. We should be able to calculate it from what we observe. So we decided to write a scaling law. And this is what came out. This is a paper that's unpublished at this time. I'm publishing other papers in the scientific journals right now that are the foundation of the change I've made to Einstein field equation. This will follow. We presented this at the American Physical Society in Albuquerque, and here and I've presented it as well to some of the directors of the telescope here on the Big Island, and many other astrophysicists and physicists. And usually I get a pretty good reaction out of it. It's kind of, you know, jaw-dropping. What we did is we took the radius of objects, okay? And so here on the in the x-axis is the radius. And here is the frequency of these objects, the fundamental frequency of these objects in hertz. And the energy level of the object is pretty well described by its frequency. So you could think of its energy level as well. If you take the size of the universe, that is, if you look at the way the universe is expanding, you can extrapolate its size. And if you look at all the matter that's in the universe, when you place that amount of density, when you place all that matter in Einstein field equation, the result is that the universe is too dense for light to escape it. That is, we live inside a black hole. And, you know, that was expected from me. I thought that earlier, and then I realized that as well from my own calculation before, and I thought that would make sense. Because remember, I was thinking that if for every expansion there's an equal and opposite contraction, then everything can be divided to infinity, then everything would have infinite density at its center. Everything would have what we call singularity at its center. And so I thought everything is just a different size black hole. And so I wasn't surprised about this. So we placed the data point for the universal, the 10 to the minus 17 is the universal frequency based on our calculation, and the radius is 10 to the 28. And then we place the next data point for quasars. We're taking average size and frequencies of quasars. This is a very large scale, so it's acceptable. And we place the data point. And it surprised us. It was a fairly good linear progression from universal size. Then we place the data point for galactic centers. So we're getting smaller in scale. And again, an average galactic center, oscillation rate, and radius. And we place the data point, and again, linear progression. Then we place a data point for solar dynamics, stellar dynamics, and we got a linear progression again. That was astonishing. I mean, there is nothing in standard views that would predict that, other than the view I was getting that the vacuum is dividing itself under very specific structure boundaries. Then we went all the way to the atomic level with the radius and fundamental approximation of frequency for X-ray emission. And we got a data point that was a perfect linear progression, again, but this time across the boundary of quantum theory into the atomic level. So now we went from cosmological object to quantum theory level. And this is one of the fundamental fractures in our current physics. Quantum theory and relativistic physics don't agree. They don't work for each other. So that was really exciting. And then we went all the way down to the Planck's lengths and placed the Planck's length dot data point and at 10 to the minus 33. And sure enough, the progression was perfect. And that got us very excited. I mean, definitely it supported what I was trying to explain to Elizabeth and our discussion, and we started to really get some steam going, and it was really exciting to see that happen. And we thought of publishing it, but I wanted to publish first very fundamental physics to be able to explain this, not just the phenomenon. The other thing we noticed is that if you take the distance between the data point, which is kind of nice, it's sweet, and you divide them, you always get very close approximation to the phi ratio. The phi ratio is 1.618 and is, and goes to infinity. It's typical to find it in nature everywhere. You find it in flowers, in shells, in pine cones. You find it in the way tree divides. You find it in your body. There's a phi ratio between the end of your finger and the second part of your finger, and there's a phi ratio between the second part and the third part and your hand, relative to your fingers, and then your fingers and hand relative to your forearm, and your whole body is built like that, and so on. And so you find it in nature everywhere. So to find it on a scale that's so large was very exciting because it supported that this would be something that nature would naturally do, that space, that the vacuum would naturally divide itself under these very specific fundamental mathematics because we observe it in nature everywhere. And so it confirmed to us a lot of it. Now, this was my presentation at Albuquerque, and I'm going to add a little data point for our benefit here. I didn't do that there because it could you could freak out a few physicists. So the physicists in the audience, please don't freak out. But if you actually add a data point for the biological resolution, what I call the biological resolution, that is the size of the sphere of our cells and their frequency level. Now, this research has shown that there's definite resonance match at approximately 10 to the 11 for the frequency of lipoprotein of the boundary of cells. So that means the cell's boundary, all right, the surface of cells in the biological level oscillate at 10 to the 11 hertz. I mean, that's a massive oscillation. And it's funny because when we think of biology, we always think of some really kind of glooby, kind of blobby thing that's moving really slow, right? But actually, the surface, when you look on the surface oscillation of these cells, it's very intense, a lot of energy. And it just happens that if you take 10 to the 11 hertz and you take the radius of a cell and you apply that much energy into that radius, if you solve that with relativistic physics, the cell obeys the Schwarzschild condition. That is, the cell obeys the condition of a black hole. Okay, I'm not, don't panic. It's okay. But what I'm saying is that we're still dealing with the same fundamental dynamics, even at the biological level. And certainly, there's not any biology in Einstein field equation, and there's no biology in quantum theory. And, this link to biology has been looked for a very long time. Well, we were happy to find that if you place that data point for the biological cells on the graph, it would